Good morning, everyone. Good morning, everyone. And how are you all doing? I hope you all are doing good and your preparation must be to the point and spot on. Great. So let me give you an outline, a blueprint of what we are going to do today. Today, we'll try to cover up quantum numbers. Okay. Second thing, we'll try to cover up concentration terms. And then we'll go with the real gases. And as far as thermodynamics is concerned, no voice?
No voice.
Okay, wait. Am I audible now? Audible to all of you? Am I audible? Good morning, everyone. Am I audible now? Now okay? Okay. Okay. Great. Good morning, everyone. Good morning. So I was just giving you the outline of what we are going to do today. And today we'll be discussing the quantum numbers, concentration terms, real gases. And as far as thermodynamics is concerned, we'll try to go with, say, entropy change and delta G. And as far as chemical equilibrium is concerned, we'll discuss Lee-Chatelier's principle, okay? Principle. And then last but not the least, we'll discuss the solubility product. Hai na? So these are the topics we are going to discuss. And one more thing is remaining, that will be regarding the redox thing. So I'll tell you something about the disproportionation reactions over there. So that is the content we are going to discuss today. This is important one. So please pay attention and we are going to begin now. Okay. So let's begin first with quantum numbers. Okay. So when you solve Schrodinger wave equation, you get three solutions of that, and they are N, L, and M. This is called principal quantum number. This is called auxiliary quantum number, and this is called magnetic quantum number. And the fourth quantum number, that is spin quantum number, this does not come from Schrodinger wave equation. From Schrodinger wave equation only these three quantum numbers come. This is given when we apply theory of relativity to Schrodinger wave equation. Okay, now see this thing. All these quantum numbers, they are in hierarchy. N will decide the value of L will decide the value of M. So for example, for a given value of N, the value of L can be from 0 to N minus 1. And as far as the value of M are concerned, for a given value of L, M value can be from minus L to plus L. Okay. Now let's go a little bit deep into it. Like say I'm going to give you a rough idea what the thing is like that. Say for example, this is the nucleus. This is a very rough idea. It has got nothing to do with the reality. Say for example, we are having a shell. There are a number of shells actually. There are a number of shells. So say I'm talking about this shell. So this shell will contain certain subshells. Okay, but this is a very crude idea, not a fair idea. Okay. Now these subshells in a given subshell will contain certain orbitals. In these orbitals, the electrons are located. Okay, it's a rough idea. So a shell will decide the idea about the subshells. The subshells will decide the number of orbitals. In these orbitals, we have got electrons to live in. Okay, now see that if I talk about N, the principal quantum number, this principal quantum number actually decides the energy, the size and the name of the given shell. Okay, so let's say how we are going to define this stuff. So for example, if I have got N equal to say 0, 1, 2, 3, 4 and so on, in that case, the name of the shell given will be, for 0, we'll call it K shell, L, M, N, O and so on. Getting it? Okay, now regarding the energy, we all know that energy of an electron in a given shell is given by minus of 13.6 into Z square upon N square. And as far as size is concerned, we know that let's not say 0, say like say 1, 2, 3, 4, 5 and like that. Okay. So first shell will be given by K. Okay, so in the first shell, if I took about so energy will be given by the value of Z and the value of N. But if I'm looking for the size, as the number of N increases, what will increase? The size of the shell will increase. Say for this is a nucleus, for N equal to 1, this is the size of shell, N equal to 2, N equal to 3, N equal to 4 and so on. The size keeps on increasing as the value of N will increase. Now, very important, one more thing. This value of N also determines the angular momentum. The angular momentum of the electron, which is given by mvr is equal to n h upon 2 pi, where n is any natural number. N will be equal to say 1, 2, 3 and so on. Are you getting that? So angular momentum of an electron is nothing but integral multiple of h upon 2 pi. So for example, if I ask you a question, which of the following statement are correct regarding the angular momentum? For example, first option is that mvr, that can be equal to say or we can say that say 2.5 into h upon pi. Second one, mvr, is it possible to have like say 3.5 into h upon pi, or say we can have mvr is equal to h upon pi? Which of the following is correct? So let's see that. I mean, never ever judge the answers of this kind of questions on the basis of that it is a multiple of h upon pi. No, we have to make sure that they have to be the multiple of h upon 2 pi. Until and unless you are able to balance it to h upon 2 pi, don't give your answer. For example, in this case, this can be written as 5 into h upon 2 pi. I am multiplying and dividing by 2. So this will become an integral multiple of h upon 2 pi now, which is actually a correct value. Similarly, over here it will be say 7 into h upon 2 pi. So again, this is the integral multiple of h upon 2 pi, where integer is what? 7. And here also this will be say 2h upon 2 pi. Again, it is the integral multiple of h upon 2 pi. So all these statements are correct regarding angular momentum. No, all of them are correct. All of them are correct. All of them. Okay. Varshini, Gagandeep. Getting that, everyone? Okay, good, great. So now let us come to the secondary or auxiliary or angular quantum number that is given by, say, L. But before I come over here, I just want to tell you one thing, that for a given shell, if I talk about number of subshells, they will be given by n itself. And if I talk about the number of orbitals in a given shell, it will be given by n square. And if I talk about number of electrons in a given shell, they will be given by, say, 2n square. In each orbital, we have got 2 electrons to survive. So the number of electrons will be 2n square. Getting it? Say, for example, if I have got n value equal to, say, maybe say 4, then how many subshells will be there? 4 subshells will be there. And number of orbitals will be 4 square. 4 square means 16. And if I talk about the number of electrons in n equal to 4, they will be 16 into 2. That will be 32 electrons. Are you getting that? So which subshells will be there? It will be 4s, it will be 4p, 4d, and 4f. 4 of them. Is that clear? Now, if I look at the number of orbitals, S will have only 1 orbital, P will have 3 orbitals, D will have 5 orbitals, and F will have 7 of them. Are you getting that? 1, 2, 3, 4, 5, 6, and one more 7. Getting that? So if you will total that, 1 plus 3 plus 5 plus 7, they will be all 16 orbitals. And in each orbital, maximum number of electrons possible are 32. 16 into 2. Getting that? Okay, good one. Very good. Okay, now come over here. Let's say go with the angular quantum number or secondary quantum or auxiliary quantum number. Okay. So this is actually L. L will decide the shape of the orbital, and also it will define the energy of a subshell. Are you getting that? So how come the energy? Sir, you have just told that energy was given by actually minus of 13.6 into z square upon n square. Yes, and decides it, है ना? But according to quantum theory, we have got a subshell also. The energy of subshell will be given by the value of L. There is something called N plus L rule also. For multi-electron species, we have got N plus L rule. I'll discuss this rule in a short while. Wait for that stuff. Now see this thing. The value of L will depend on the value of N. For a given value of N, the value of L can be from 0 to N minus 1. Are you getting that? Okay, we'll do some questions of that as well in a short while. Like say, angular momentum. We have just seen that angular momentum, which is given by N. If I have a prefix before it, it is called orbital angular momentum. This will be given by root of L into L plus 1 h upon 2 pi, where L value will be 0, 1, 2, and 3, and so on. For L equal to 0, we call it S, P, and D, and F subshell, and so on, okay? So tell you one thing, for S subshell, what is the value of the orbital angular momentum? It will be put L equal to 0 for S, it will be 0 into 0 plus 1, and h upon 2 pi. So when you multiply anything by 0, will become 0. That means the orbital angular momentum of electron in a S subshell is 0. Okay. And for P, it will be put 1 plus 1, and h upon 2 pi, which actually equals to root 2 h upon 2 pi. Simplified, it will be h upon root 2 pi. Is that clear? Similarly, you can find out the orbital angular momentums of other subshells as well. Say for D, I'll solve it again. This will be 2 into 2 plus 1. H upon 2 pi will be equal to root of 6 h upon 2 pi. How much? This will be root of 3 by 2 h upon pi. Getting it? So all of these you have to learn by heart. Okay. So there is no point in solving out there. If you do this homework, it will be easy for you to handle the questions on the orbital angular momentum over there. And they will be asking you either S, P, and D. The chances are very high. Okay. Okay, now let's go with this thing. Like say for a given value of L, if I ask how many orbitals will be there, this L denotes subshell. In a given subshell, for a given value of L, how many orbitals will be there? It will be 2L plus 1. Okay, and how many electrons will be there? It will be, for because these are number of orbitals. These are the number of orbitals. How many electrons are possible? Maximum number of electrons in a given orbital is 2. So these many orbitals are there. So total number of electrons will be 2 into 2L plus 1, which can be written as 4L plus 2. Okay, so these many electrons are possible. These many electrons are possible for a given value of L. Okay. So let's say we have got say L equal to 0, L equal to 1, L equal to 2, L equal to 3, and so on. This will be like say S, this will be P, this will be D, and this will be say F, and so on. So if I talk about number of orbitals and number of electrons in a given subshell. Okay, so for L equal to 0, number of orbitals calculated 2L plus 1. So this will be only 1, this will be 3, this will be 5, this will be 7, and number of electrons will be, maximum of electrons will be, in each orbital we have 2 electrons. So 1 into 2, 2, 2 into 3, 6, 10, 14, and so on. So the difference is of 4 actually each time, successively. Getting it? Good one. Chalo, theek hai, aa jao. Now we come to the value, this called M. This is called magnetic quantum number. It describes basically the orientation of angular momentum. Okay. So like say this value of M is decided by the value of L. So for a given value of L, the value of M can be from minus L to plus L. From minus L to plus L. Okay. So let me tell you one thing. Like say if I have got L equal to 0, the value of M will be from minus 0 to plus 0. Minus 0 to plus 0, which means actually nothing but 0 only. There is only one value. For this one value, we have got actually say one orbital. L equal to 0 means S. So in S subshell, we have got only one orbital. Similarly, if I go with L equal to 1, which means actually P subshell. So value of M will be from minus 1 to plus 1. Minus 1, 0, and plus 1. All of them will be integers. Okay. So there are 3 values. For these 3 values, we have got 3 orbitals. This will be say Px, this will be say Py, and this will be say Pz. I mean, according to IUPAC, the value of M equal to 0 is given to the orbital along the z-axis, while these value can be exchanged. Okay. Okay. Similarly, if I go with L equal to 2, which means what? The value of M can be from minus 2, minus 1, 0, plus 1, and plus 2. There are 5 values, and all these 5 values are denoting each orbital. So this can be like say dxy, this can be dyz, this can be dzx, and this can be dx square y square, while this will be dz square, because according to IPAC, the value of M equal to 0 is given to arbitrarily to the orbital along the z-axis, dz square, and these values can be exchanged. Okay, these values can be exchanged. Getting it? Okay. Okay. Like say now the last one, that is called spin quantum number. First of all, understand it is purely a quantum phenomena. It has got no classical analog. I mean, that means I cannot explain this spin quantum number by giving you any example, any physical example which we see in daily life. So if I ask you the value of S, which means what? It means the spin of the electron is say up or down, or say clockwise, or say anti-clockwise, or say plus half, or say minus half. So which is the correct value for this one? This is the first option, second option, and third option. Which will denote the true things about the S, spin quantum number? Up and down spin, clockwise, anti-clockwise, or plus half or minus half? Which of the following is correct, or all of them are correct? The fourth one is say all of them are correct. All of them are correct. All of them are correct. Okay. See, these are incorrect denotation. These are the only values which are correct for, no, not all are correct. Only this one, third one is correct. They are not correct. They are simply signifying, I told you that this is a purely quantum phenomena. I cannot explain the value of S or the significance of S by giving you any physical analog or any classical analog or say any physical example. Getting it or not? Electron, basically, we cannot say it is going up and down. There is nothing like that. We cannot say it is going anti-clockwise or clockwise. No, not at all. Only one thing is a purely mathematical construct. Purely mathematical construct. So S, when they say plus half or minus half, that's the only true significance of that stuff. Are you getting that? Okay. Okay, now see, this value of S will also give you spin. Spin angular momentum. Okay, spin angular momentum. Just like the mass of electron or charge of electron, which any electron which whenever it will take a birth, it will come along with the mass of electron, charge of electron, and one more thing that is called spin of the electron. It's the intrinsic property of electron. So if they ask you what are the three intrinsic properties, mass, charge, and spin of the electron. Okay, if electron is not having a spin, that means it's no more electron now. Okay, so this is actually given by root of S into S plus 1 H upon 2 pi. Are you getting that? Getting that? So over here, the value of S, you always have to take plus half. You cannot take minus half value because this is not allowed. Otherwise, you'll get an imaginary spin angular momentum, which is not allowed actually. Na? So when you put the value of S equal to half, you will get this value as root 3 H upon 4 pi, which is actually fixed. For all electron, the spin angular momentum having this value is fixed. This is the fixed value of all the electrons, which will have this value of spin angular momentum. Is that clear? Okay. So that we have done now. So can we solve some questions now regarding the quantum numbers quickly? Before that, one more thing, tell you one thing. What is Pauli's exclusion principle? Pauli's exclusion principle. Come on. See, over here, we have to be very sure that what we are reading, okay? So Pauli's exclusion principle, tell me one thing, whether I'm speaking correct or not. According to Pauli's exclusion principle, no two electrons can have same set of all four quantum numbers, true or false? No two electrons can have same set of all four quantum numbers, true or false? According to Pauli's exclusion principle. True. Gagandeep says true. Shyam Sundar says true. Samira Sahiti, Dikshita says true. True. Okay. Got it. False. Swaroop says false. Okay. It is actually false. You know? See, over here, no two electrons in a given atom. This is important. Given atom. For a given atom, not orbit beta. It is given atom. No two electrons in a given atom can have same set of all four quantum numbers. Getting it? If I remove this given atom, this definition will become wrong. For example, if I talk about hydrogen and I talk about, say, helium plus, say, for example, so both are having, say, one electron each. So this electron can reside anywhere. So this electron can be maybe, say, in, say, 2s orbital, and this can also be, say, in, say, 2s orbital. In that case, the value of quantum number for these two electrons might be that N, L, M, and S will be 2, 0, 0, and suppose this is a plus half. But this electron, over there, N, L, M, and say S, this can be 2, 0, 0, and this can be, say, plus half. But this will be in the different atom. Are you getting that? Now, if I have got, say, like, say, two electrons, if I put, say, helium and I'm going to make it, say, lithium. whatever, है ना? So the two electrons, the second electron in the given atom, this cannot have 2, 0, 0. If it is there, it has to be minus half. This cannot be plus half. But that the different electron, the second electron over there, can have this value. Are you getting that? Okay. So given atom is important out here. Given atom is important. Or the simple version of what I have said is that only 2 electrons can live in a given orbital. Is that clear or not? One more corollary of the Pauli's exclusion principle is that only 2 electrons, maximum 2 electrons can live in an orbital, and that too with opposite spin. And that too with opposite spin. Yes or no? So which of the following statement is false according to Pauli's exclusion principle? All right, which does not obey Pauli's exclusion principle? Come on, tell me one thing. Which of the following does not follow the Pauli's exclusion principle? Come on. Correct. This does not follow, I mean, because over here, the 2 electrons are having the same spin. 2 electrons are having the same spin, which is not allowed. Okay. One more thing, and that is Hund's rule of maximum multiplicity. What is the statement of Hund's rule of maximum multiplicity? Who will tell me that stuff? Hund's rule. Hund's rule of maximum multiplicity. Who will tell that? So I'm dictating it, na? Just let me know that this is true or false. According to Hund's rule of maximum multiplicity, the pairing of electron will start only when the orbitals are singly occupied. Orbitals are singly occupied. The pairing of electron will begin only when orbitals are singly occupied. True? You have to be very careful while giving the answers when they give you statement. They're the masters of language and they can dupe you into that. It is not correct. It is not correct. So I'm giving you all the things about this thing. No, it's not true. This is false. This is false. See that stuff. According to Hund's rule of maximum multiplicity, the pairing of electron in degenerate orbitals of a given subshell, very, very important, in a given subshell of a given atom. Okay, degenerate orbitals of a given subshell in an atom will begin only when all the degenerate orbitals are singly occupied. That means even that the electrons which are like singly occupied, they should have the same spin. All the electrons which are, say, singly occupied must have the same spin. For example, if I ask you a question that which of the following is not going to obey the Hund's rule, the first one, this is it, I'm going to give you. Which of the following do not follow Hund's rule of maximum multiplicity? Or there is fifth option also. Multiple options are there. Achha, multiple options are possible. I'm saying that. Okay, see that stuff. So first, clearly, this obeys the Hund's rule of maximum multiplicity. Yes or no? When I say degenerate orbitals, this px, py or pz, they all obey. They're all obeying the Hund's rule of maximum multiplicity. The reason is that over here, all of them are having same energy, same energy. This px, py, pz are having the same energy. So electron can go anywhere. It can go first here also, and here also. Yes or no? And once this is done, the pairing can again begin anywhere. It can begin here, it can begin here, it can begin here only. There is no rule that you have to first fill the px. No, it's not possible. Yes or no? So we can begin from here, we can begin from here also. But the thing is that whenever you are filling the orbitals, the first electron which is going into the orbitals individually, it has to have the same spin. Are you getting that or not? So this is correct. But over here, this one is having the down spin. This is not allowed. They should have the parallel spin, same spin. Whenever we're talking about the singly occupied orbital, they should have same spin. So this is not correct. Over here, this is perfectly correct. No problem with that stuff. And this is not correct. The reason is that you cannot begin pairing once this is also filled. This will be okay if I make it something like this. This will be okay now. Without this thing, this will be incorrect. So 2 and 4. Is that clear? Okay. Okay. Now let's do quickly, like say, one question that for n plus L equal to 7, how many subshells are possible? How many subshells are possible for that? Come on, be quick. N plus L equal to 7, how many subshells are possible? I know one thing, that n value can be 7 and this can be 0. This will be 7, 6 plus 1, 7, 5 plus 2, 7, and we can have 4 plus 3, 7, 3 plus 4, 7, then 2 plus 5, 7, 1 plus 6, 7, and 0 plus 7 equal to 7. But I know that the value of L, are you in that? Sorry, from here onwards. The value of L cannot be more than the value of n. So these values are not possible. These values are not possible. Only this, and this, and this are possible. So this will be n equal to 7, L equal to 0 will be what? 7s. This will be 6p, and this will be 5d, and that will be 4f. So 4 subshells are possible, which are 7s, 6p, 5d, and 4f subshell. Is that clear? And if I ask you for this equation, how many orbitals are possible? How many orbitals are possible? Come on. For 7s, only one orbital. For 6p, there will be 3. And d, 5, and then we will have 7. Yes or no? So total will be 16. 16 orbitals are possible. And if I ask you maximum number of electrons possible for this, they will be 16 into 2. That will be equal to 32 electrons. Yes or no? 16 orbitals and 32 electrons. Great. Chalo, okay. That is done. Now they ask you one question that this psi 420, which orbital is denoted by psi 420? Come on. This 4 is value of n, this is say L, and this is say M. So n equal to 4 means we are in the 4th shell, L equal to 2 means we are in D, and M equal to 0 will mean along the Z axis, 4D Z square. Yes or no? Similarly, psi 310 will denote which orbital? Come on. N, L, and M. 3rd shell, L equal to 1 means P subshell, 3P, and M equal to 0 means along the Z axis, PZ, 3PZ. Good, very good, very good. Very good, good one. Now tell you one thing, when I give you N value, L value, and M value, what exact information I am supplying to you people? How many orbitals will these 3 quantum numbers together will denote? 1 orbital, 2 orbital, 3, or anything possible. N, L, and M, they will denote basically 1 orbital, 2 orbital, 3, 4, or like anything is possible. 1 orbital, na? We have seen in these questions, and whenever we are having the value of n, l, and m, we are having the exact value of 1 orbital or location of electron. Okay. Acha, when I give you the value of n, l, m, and s, I'm giving the exact information of a single electron, But when I give you the values of n, l, and m, I am giving you the information of 2 electrons. Yes or no? Because in each orbital we have maximum 2 electrons. If you want location or not location, exact information of electron, you will need s also. Getting it? So tell you one thing, how many electrons will live in, say, 6p orbital? In 6p orbital, how many electrons will live? In 6p orbital, come on. Two. Whenever you find a word called orbital, it means only 2 electrons, है ना? Only 2 electrons are possible. Okay? Chalo, ठीक है. Okay. Okay. Okay, now let's come to the concentration terms now. Okay, so very quickly we'll go through that stuff because certain things you know already. I'm going to solve certain questions which are like interconversion of the concentration terms. Okay, will it do it? Chalo, theek hai. I believe that everyone knows that molarity will require volume of solution in liter, and molality small m will require weight of solvent in kg. Be careful with this m, small m. So I'm going to do certain questions which will be all about interconversion of the concentration terms, because concentration term by now, so all of you must have been information about. Chalo, theek hai. So if they give you the molarity, how you will find out the molality? So molality will be given by 1000 m upon 1000 d minus m into mb. Boys and girls, I mean, at least for this lecture, but I'll mean A will be given as solvent and B I'll denote as solute. Please understand that stuff. Na? A will be solvent and B will be solute. Okay, where this capital M is molarity and this MB is actually molecular weight of the solute. D is the density of solution. Okay, and then there is one more conversion, that is for this molality itself. When they give you mole fraction of solute, this will be given as 1000 xi b 1 minus xi b into Ma, where Ma is molecular weight of solvent. So let's do a question on both of them. Okay, so let's do that quickly. So over here I'm giving a question that we are having 18 molar H2SO4 solution. 18 molar H2SO4 solution whose density is given as 1.8 gram per ml. You have to find out molality of this solution. So what I'll do, I'll simply put M equals to 1000. Molality is what? 18. And then 1000 into density. Density is what? 1.8 into 1.8 minus of M, capital M, is 18 into MB, molecular weight of solute. That will be 98. Yes or no? So while solving all these questions, I'll recommend that please don't try to solve in every step. Take the calculation to the last one, okay, and then solve it there. So can I simplify that stuff as 1000 into 18, and this is 1.8, this is 1000. Can I remove this? And this will become now 100 into 18 minus 18 into 98. If I do 18 into 98, it might be disastrous for me here, and I will be wasting a lot of time. But what I can do one thing, that I can take 18 common. 1000 into 18, this will be 18, and 100 minus 98. Now one thing happens, this clearly goes off. 100 minus 98 is what? How much? 2. And this will be 500. So my answer will be 500. As easy as that. Is that clear? It will be 500. We have to be very quick at that stuff, okay? So let me give you, like say, one more question. I'm giving you the mole fraction of urea, that is a solute, na? Mole fraction of urea is given as say 0.2 in benzene solution. In benzene solution, right? That means the benzene is what? The solvent. So you have to find out the molality. Here Xib is given to you. Here Xib is given to you. So use this formula: 1000 into Xib, 1 minus Xib into Ma. Ma is the molecular weight of solvent. Solvent here is what? Benzene. So I can write down 1000 into Xib is how much? 0.2. 1 minus Xib will be 0.8 into, this is 78. And this will be 4 times, this will be 250, and I can write down this as 250 upon 78. Okay. If you look at the options, and options are like bit far apart in terms of values, I can make some approximation. This will be 250 upon 80. Okay, yes or no? I can do that. Okay, this will be almost 3.1. I know what 8, 3, 24. So the 3.1, 3.2, whatever it is, like say. See your answer, mark it and move ahead. If the options are quite far apart, okay? Generally, they will be quite far apart as well, okay? Okay, now one more thing I want to say over here. There is something called percentage weight by weight and percentage weight by volume. Remember that this numerator is for always solute. This denominator is always for solution. Always for solution. Okay. Now, what is the meaning of this thing? 9.8% weight by weight H2SO4 solution. Come on. And what is the meaning of 9.8% weight by volume H2SO4 solution? Say for example, okay? So it actually means, this means 9.8 gram H2SO4 solute in, this will be, whenever you do percentage is always done on 100. So 9.8 gram of H2SO4 in 100 gram of solution. This is weight, this is weight. The both must be in terms of weight. Is that clear? Similarly, over here, this means 9.8 gram. This is weight, na? Gram of H2SO4. This is volume in 100 ml of solution. In 100 ml of solution. Here it is 100 gram of solution. Here is 100 ml of solution. Getting it? So if they give you this stuff, you have to find out the molality, small m. Can you find out? Can you find out the molality, small m? The small m out here will be how much? Because we know the molality is what? It is basically weight of solute upon molecular weight of solute. And over here it is the weight of solvent in gram, then multiply by 100. Yes or no? So 1000 by 1000. Okay. 9.8 gram of H2SO4 and 100 gram of solution. This is solution. This is solute. What will be the weight of solvent? It will be 9.8 minus, 100 minus 9.8. It will be how much? 90.2 gram. 90.2 gram. Come on. This will be 9.8 into 1000 upon, what is the MB? 98. The solute is what? H2SO4. So MB will be 98. And weight of solvent 90.2. This will be 10 times gone. 100 by 90.2. I mean, I can remove this stuff. 0.2 doesn't matter much. So this will be 10 by 9, almost 1.1. Almost 1.1. You will get your approximate answer over there. Okay, in physical chemistry, they don't give you that close answers. You know? Only one question at max will be there, which we can do to the exact point when the time will come. Now over here, you have to find out the molarity, the capital M. Capital M is what? It is WB upon MB. Volume of solution, if it is given in ml, I'll multiply by 1000. So weight of solute is how much? 9.8 gram. 98, yes or no, into 1000. And that will be 100. This is gone. This is also gone. This will be 1. So this is the 1 molar solution. But the molarity is what? 1.1. So that is the okay directly. So whenever they will give you percentage weight by weight, they'll ask you molality. Whenever they will give you percentage weight by volume, they'll ask you molarity. But if they give you this stuff and they ask you molality, or they give you this stuff and they ask you molality, in that case, the examiner will also give you the density. So let's do a question on that. Okay, let's do a question on that. So I'm giving you that question is there. It says, what I can say. Okay, we have got 10% weight by weight, 10% weight by weight NaOH solution, which means an aqueous solution, है ना? And density is given as 1.2 gram per ml. 1.2 gram per ml. Okay, you have to find out the molarity. Capital M. You have to find out the molarity. From this, though, you can easily find out the molarity, small m. But if they ask you molarity, okay, what you will do? Because for molarity, I'll require volume of solution. Volume of solution will be what? Weight of solution upon density. Weight of solution upon density. Is that clear or not? So what is the meaning of this 10% weight by weight NaOH solution? I mean, this actually says this is 10 gram of NaOH in 100 gram of solution. So over here we have got 100 gram of solution. Density they have given you. Can you find out the volume of solution? So from here I can find out volume of solution. Volume of solution will be what? Weight of solution upon density. Weight is 100 gram and density is 1.2 gram per ml. 1.2. So this is the volume of solution given to me. This is the weight of solute. Now molarity I can easily find out. What will be? Weight of solute. That is how much? 10 gram. Upon the molecular weight of solute, how much? 40. Volume of solution 100 and 1.2 into 1000. That's whenever volume is given in ml, I'll multiply by 1000. So I believe this will all be gone. This can be carried off. This will be 3. So capital M molarity will be 3. Is that clear? Is that clear to all of you? Okay. Okay, good. Very good. I'll tell you one thing. Which of the following is independent of temperature? Which of the following concentration term is independent of temperature? First one, molarity. Second one, molarity. Third one, mole fraction of solute. Fourth one, I'm giving you percentage weight by weight. Which concentration term is independent of temperature? Come on, everyone. Independent of temperature. All of them are independent of temperature. Anything which depends on volume, because on changing temperature, you can change volume. If you change temperature, I can change volume. So molarity is the only stuff which requires volume. Rest of them, all of them are basically based on weight itself. There is no concept of volume in all of these three. Yes or no? This is all weight. This is also number of moles and number of moles. Number of moles depend on, particles only. They don't depend on number of moles. And molarity also depends on the weight. Is that clear? So except molarity, capital M, all of them are independent of temperature. Yes or no? Chalo. Now let's come to the real gases. Okay. So we have one thing, ideal gas and real gas. The real gas differ from ideal gas in two aspects. First one, that over here intermolecular forces are 0. Here the intermolecular forces are not 0. Second one, the molecular volume. The molecular volume is also 0. Here it is not 0. Remember this very, very important stuff. On these two aspects, the real gases differ completely from ideal gases. Okay. Now we all know that PV is equal to nRT for 1 mole of ideal gas. For 1 mole of ideal gas, PV will be equal to RT, and this PV upon RT is actually called Z. This will be equal to 1 for 1 mole of gas. Will be equal to always 1 for 1 mole of ideal gas. This is always 1 for ideal gas. But Z is not equal to 1 for real gases. Is not equal to 1 for real gases. This Z may be more than 1. This Z may be less than 1. for real gases in general. Now let's see that stuff. See, this Z is also given by V real upon V ideal, volume of real gas upon volume of ideal gas. Okay, volume of ideal gas. I mean, say that if this Z is less than 1, if this Z is less than 1, that means V real is less than V ideal. Okay, and if I talk about STP, the volume of ideal gas at STP for 1 mole of it will be 22.4, will be 22.4. That means V real will be less than 22.4 liter. Agree or not? Whenever Z is less than 1, volume of real gas is less than 22.4. So if I'm compressing the ideal gas and the real gas, I'll able to compress the ideal gas till what? 22.4 liter. But I'll be able to compress the real gas for a volume less than 22.4 liter. That means the real gas is more compressible. Real gas is more compressible. Remember that whenever Z is less than 1, Z is less than 1, the compressibility of real gas is more. Are you getting that or not? Whenever Z is less than 1, the compressibility of real gas is more. And similarly, if Z is more than 1, in that case, V real will be more than V ideal. Agree or not? And at STP, for 1 mole of the gas, V real will be more than 22.4 liters. Agree? That means when Z is more than 1, the volume of real gas is more. I'm not able to compress it. Okay, comparatively. That means the compressibility of the real gas is less. I'm not able to compress the real gas. Getting it? Okay, now see this stuff. Whenever you plot a graph of this Z equal to 1 out here, this is Z increasing, decreasing, and here we've got pressure. Generally, the real gases, they go down over here and then they go up. They go down and then they go up. Okay, and again down and up. So if except for 2 gases which are like say hydrogen and this is say helium, all other gases, they will take a dip and they will then come up. Now here is the significance out here. This Z is equal to 1. Below this thing, Z is less than 1 and here Z is more than 1. Z is less than 1 over here because over here intermolecular forces dominate. Is that clear? They will dominate. And Z is more than 1 because over here the molecular volume will dominate. Remember these things, they will come directly as it is. Now this is curve number 1, this is curve number 2, this is curve number 3. Which gas will deviate more from the ideal behavior? Gas number 1, 2 or 3? Now the curve which goes more down and then goes up is deviating more. Yes or no? Will deviate more. So third curve is going deeper and then going up. Yes or no? That means over here the intermolecular forces are very high for third curve. So IMF, if I say IMF number 3, IMF number 2, IMF number 1, intermolecular force in the curve number 3 is more than the IMF in the curve number 2. Is that clear? Is that clear? So we have now one thing, that van der Waals equation, which is the correction of the ideal gas equation. I mean, this PV equal to nRT, this is valid only for ideal gases, not for real gases. And if you want this kind of an equation to work for the real gases, we have to modify it. This is for ideal pressure, this is for ideal volume. Okay, or say free volume. So for real gases, van der Waals modified it and said AN square upon V square into V minus NB is equal to nRT, where this is called ideal pressure, this is called ideal volume. This thing is called pressure correction, this thing is called volume correction. Is that clear or not? This pressure is called the pressure of real gas. This volume, this V is called volume of container. Remember that stuff. Yes or no? Getting or not? Okay, now see one more thing over here is very, very important. This A decides intermolecular force and B decides molecular volume. Molecular volume. Higher the value of B, higher is the molecular volume or the size of the molecule Higher the A, higher the intermolecular forces. Higher the A, higher the intermolecular forces. That means if a gas is having higher value of A, it means what? In which of the following cases, 1, 2 or 3, the value of A is higher? Value of A is higher. In which of the following curve, the value of A is higher? Third. Third, very good. So in the case of third, I know that higher the value of A, higher is the intermolecular force of attraction. If A is higher, IMF is higher, which means what? The polarity of the gas will also be higher. Polarity of the gas will be higher or not? Yes or no? If the polarity of the gas is higher, that means its boiling point will also be higher, because the gas particles, they will be pulling each other strongly and it will be difficult to break the bond. So before leaving into vapor, I mean, we have to give them higher temperature. Yes or no? And also, if boiling point or the polarity is higher, can I say that the ease of liquefaction, is also higher? The gas can be easily liquefied. IMF is higher, so they will be able to attract each other. So what a difference between a gas and a liquid? Whenever the gas particles are far, I mean, when the particles are far apart, they will form a gas. When I bring them closer, they will become liquid. So the particles which are having more intermolecular force of attraction, they will be able to pull each other more closely, more strongly, and they can be easily liquefied. Yes or no? So the ease of liquefaction is also more. Next one, tell you one thing. What about the value of Z? If the IMF is higher, the value of Z, you can see over here, the value of Z goes down. If IMF is higher, value of Z goes down. So that means the value of Z decreases. Yes or no? If the value of Z decreases, the compressibility of the real gas increases. Compressibility of the gas, real gas will increase. Very good, very good, very good. And what about the tendency to get adsorbed on the surface of any given adsorbent? It will also be higher, because if there is no IMF, they will not stick over here. More is the IMF, they can stick over there. Yes or no? So adsorption will also be higher. Yes or no? Good one, good one. So shall I tell you one thing? For which gas the value of A will be higher? Say hydrogen, helium, say NH3, and say CO2. For which gas the value of A will be higher? More the polar gas, more is the value of A. That will be NH3. That will be NH3. Good one, very good. So which gas will be most easily liquefied? Which gas will be more easily liquefied? NH3 only. Higher the value of A, higher the IMF. Yes, very good, very good. Acha, which gas will be having the lowest value of Z? NH3 only. Yes or no? Which is more polar? NH3 only. Which can be easily adsorbed on surface area? NH3 only. Okay, now? Similarly, tell me who will have the highest value of B? The size of the molecule. Na? The first one is hydrogen. Second one is say helium. Third one is say CO2. Fourth one is say SO3. Which will have the highest value of B? SO3, anyone can see that? Bigger the molecule, higher the molecular volume, size of the molecule. Right? So bigger the size of the molecule, bigger is the value of B as well. Getting it? Chalo, theek hai, aa jao. Now there is something called Boyle's temperature. So Boyle's temperature says that let's have the value of Z equal to 1, Z equal to 1, and we all know that a real gas will behave like an ideal gas at higher temperature, yes or no? So this is say pressure and pressure out here. This is Z equal to 1. And a typical real gas is having this kind of a curve at temperature T1. So if I increase the temperature to T2, I believe this curve will shift up, है ना, as I increase temperature. So it will try to behave more like an ideal gas. But if I increase the temperature to T3, it will further move up and almost behave like an ideal gas, at least for this much of pressure range. And then it will deviate. So this temperature T3, for which a gas, real gas, behaves like an ideal gas for a given range of pressure. For a given range of pressure is called Boyle's temperature. Okay, so this TB, Boyle's temperature, is given by A upon RB. So they will give you the value of A and B, and accordingly they can ask you the Boyle's temperature also. Okay. Now there is something called critical temperature. So this graph is very important. This is say pressure, this is say volume out here, and you must have seen this in NCERT also. So at a given temperature, this curve is going on like this. T1, and at further higher temperature T2, you will see that this curve is something like this, and then like this. At T3, again, this is something like this, and then going up. And there is just an inflection point is there. So this zone is actually the zone of the gases. This is T1, this is T2, this is say T3 over there. And over here we have got gas plus liquid, and gas plus liquid out there. And over here, this is all liquid, and liquid. So what is the significance of these curves? Say from point number 1 to 2 to 3 and say 4. From 1 to 2 point, I am increasing pressure. As I increase pressure, the volume is decreasing. But at the same pressure, I can see that volume is decreasing, but I'm not increasing pressure from point 2 onwards. The reason is that in this zone, the intermolecular force of the gases is working. So I don't need to do extra work. The particles are so close that they will attract each other now. So they don't require any external work. So here the gas is liquefying. And by this point, the entire gas is liquefied. And you can see that even if I'm applying a very high pressure, I'm not able to decrease the volume because liquids are almost incompressible. Are you getting that? So in this zone, we are having liquid and gas. This point is called critical point. This temperature is called critical temperature. And if I have a T4 higher than T3, I can see that this will follow almost an isothermal curve. This will almost behave like now an ideal gas, almost like an ideal gas. But at this point, this temperature T3, I can see that there is no difference between the liquid phase and the gaseous phase. There is only a single phase. I will not be able to differentiate between liquid and gas phase. Yes or no? So this point, this PC is called critical pressure. This VC, this is called critical volume. And this temperature itself is called critical temperature, which is given by 8A upon 27 RB. This is given by 3B, and this will be given by A upon 27B square. Yes or no? Please remember these values are very important. Also remember that this boiling point is actually 2/3 of TC. So they can sometimes ask you which is higher, boiling point of the gas or the critical temperature of the gas. So depending on, you can answer that stuff. Now there are questions which you must have seen in your grand test also. You will see that, and you must have seen in your minor test also, that they will give you value of A and B. So based on that, they will ask you the value of critical temperature. So please make sure that critical temperature from this point of view, TC, is proportional to A upon B. So you have to take care the factor of A and B, both of them. Are you getting that? The TC does not depend on only on A and only on B. It depends on both of A and B. Yes or no? And Z value at critical temperature is actually 3/8. The compressibility factor. Please remember these values. They are very, very, very important. Okay. Now also one more thing regarding these real gases. We have got, if I take for 1 mole of the gas, the van der Waals equation will be P plus A upon V square. V minus B is equal to RT. Agree or not? Yes or no? Okay, now see that stuff. So if I say if the pressure is very high, if the pressure is very high, in that case, I can neglect this factor. And the equation now becomes PV minus B equal to RT. So PV minus PB will be equal to RT. If I divide by RT, it will become PV by RT minus PB by RT, and that will be equal to 1. This thing is actually called Z. Z will be 1 plus PB upon RT. So they sometimes ask you what is the value of Z at high pressure. So that will be the value of Z. Yes or no? We all know that at Z, P very high, the value of Z is more than 1. In that graph, you could see that Z equal to 1. At higher pressure, as the pressure increases, the Z value is above 1. But at lower pressure, value of Z is less than 1. Yes or no? So whenever it has to be at high pressure, it has to be 1 plus something. Getting or not? Sure about it? And since over here I told you that molecular volume will dominate. Molecular volume is given by B. So it should contain B also, not A. But if I talk about at low pressure, volume is very high. And I can neglect this term now. Okay? So V minus B can be written as V only. This equation becomes P A upon B square into V equal to RT for 1 mole. So PV plus A upon B equal to RT. Divide by RT now. PV by RT plus A upon RTV is equal to 1. This will be Z. Z will be 1 minus A upon RTV. Are you getting that? The value of Z at low pressure is less than 1. And since over here in this region, intermolecular force dominates, which is given by A itself. So A must appear over here. It has to be 1 minus something with A there. So if you remember these things, you will be in a position to get the answers right. And for hydrogen and helium, remember that the same equation will come for both the hydrogen and helium. Z is more than 1 always for these gases. So that will be the equation over there. And that will come because over there A is very less. In these two gases, number of electrons are very less. So they don't have any real intermolecular force of attraction. Okay, so A will be almost 0. We can neglect this thing at all. Okay, same thing will come. Okay, chalo, ठीक है now. This also done. Let's come to entropy. So according to second law of thermodynamics, entropy of an isolated system, which is also nothing but universe, for an isolated system which is also nothing but universe, always increases. According to second law, the entropy of a universe always increases. Or we can say that one more corollary is there, that for any irreversible process, natural process or spontaneous process, entropy of universe is always increasing. There is third more corollary of this stuff. It is impossible to convert 100% heat into work. Some of the heat will be wasted always. We cannot convert 100% heat into work. Some of that will be wasted. Is that clear? Now, what is entropy? Entropy is a random dispersal of energy. Remember that. Entropy itself is not energy. Entropy is basically what? Random dispersal of energy. Is that clear? Now, see this thing. Now, there are two ways to define the process to be spontaneous or not. So, like spontaneity, I'm going to define that stuff either on the basis of entropy or on the basis of delta G. Remember this thing, very, very important. If you want to define the process of, the process is spontaneous or not on the basis of entropy, please, but you go with total entropy or entropy of the universe. And if you want to define the process of spontaneity on the basis of delta G, this is actually for system. If you want to define the spontaneity on the basis of system, go with delta G. And you want to define spontaneity with the help of entropy, go with total entropy. Never go with entropy of the system. Are you getting that? So if I say that for a spontaneous process, entropy of a system should always increase, true or false? entropy of system should always increase for a spontaneous process. True or false? No, it is not true. It is false, है ना? So remember that if entropy, total entropy is more than 0, the process will be spontaneous, है ना? If total entropy of the universe is actually equal to 0, the process is at equilibrium, है ना? And when entropy total is less than 0, in that case, it will be a non-spontaneous process. And if you want to go with delta G, delta G has to be less than 0. Delta G will be equal to 0 and delta G more than 0. If delta G is less than 0, process is spontaneous. Or you can say the entropy of the universe will be increasing. It will be increasing. Yes or no? And if you say delta G is equal to 0, that means process at equilibrium. That means entropy. This is delta S, na? Delta S total, na? Entropy change of the universe will be 0. Get it not? Yes or no? And delta G more than 0, it will be a non-spontaneous process, or you can say delta ST will be less than 0. Getting it? Now see that delta S total is given by delta S system plus delta S surrounding. Now I want a process to be spontaneous. In that case, delta ST should be more than 0. It is possible that this delta S system is say plus 5. Yes or no? And this is say minus 15. So total will become what? Minus of 10. Yes or no? Though this has decreased. This is less than 0. So the process will not be spontaneous. But it is also possible that this is say minus of 10 and this is say plus of 20. Even though this is decreasing, but surrounding entropy has increased more. So net is what? Plus 10, which is more than 0. This process will be spontaneous. So you should not decide the process is spontaneous or not only on the basis of entropy of the system. If you want to go with entropy, go with total entropy, not with the system entropy. Is that clear? If you want to stick to the system, that's no, sir, I want to predict the spontaneity on the basis of system only. In that case, you have to go with delta G. That is the only tool we are having in hand. But entropy, if you want to decide the process to be spontaneous or not, it has to be on the basis of total entropy, not on the basis of entropy of system, not only on the basis of entropy of surrounding, but on the basis of combined form, delta S total, which is equal to delta S system plus delta S surrounding. Is that clear or not? Yes or no? Achha, now one more thing, remember that if I say that for reversible adiabatic process, what is delta S? You all know that delta S is actually delta H upon T, and for adiabatic process, delta H is what? 0. Heat is not allowed to be transferred. So this is 0 upon T will be equal to 0. So delta S will be equal to 0, which means there is no change in entropy. This is called isoentropic process. Yes or no? Or we can say that entropy is already at max. We cannot change it even more. Okay? Okay, now one more thing. Tell you one thing. There is a state function called G equal to H minus Ts. G equal to H minus Ts. This is the total amount of heat supplied, and this is basically the total amount of energy wasted. And this is the useful energy we are having actually. Okay, so delta G will be equal to delta H minus T delta S. Getting it? Now, if you want a process to be spontaneous, delta G has to be less than 0. Yes or no? The process will be spontaneous. At delta G equal to 0, the process will be at equilibrium. And at delta G more than 0, the process will be non-spontaneous. And here, when I say delta G, I mean this delta H is of system. This delta S is again for system. I told you earlier that if you want to decide the process to be spontaneous or not on the basis of system only, go with delta G. Go with delta G. And here in this equation, this delta H is of system, not of surrounding. This delta S is of system, not of surrounding. Is that clear? So I will ask you one question basically, that if delta G is less than 0, if delta G is less than 0, the process will always be spontaneous, true or false? The process will be always spontaneous, true or false? Come on, be quick. If delta G is less than 0, the process will be always spontaneous, true or false? Everyone should answer it. This is false. This statement is false. Remember that this equation is valid only at constant temperature and pressure. At constant temperature and pressure, not always. Not always. Only if the process is occurring at constant temperature and pressure, and if delta G is less than 0, only then I can say the process is spontaneous. But if T and P are not constant, even if delta G is less than 0, there is no guarantee the process will be spontaneous. Is that clear? So please remember, as a chat lag is there. Yeah, I can see that because it's like say too late. Okay. Is that clear or not? At constant temperature and pressure, if delta G is less than 0, only then the process is spontaneous. Is that clear? Okay, now they ask you some very, very important question for delta G, that what should be the value of delta H and delta S, so that we can say safely that the process will be spontaneous or not. So let me give you one thing. This is delta H on the x-axis, delta H here, this is delta S, and this is again delta S, entropy. Okay, here delta H will be positive and here it will be negative. Here delta S will be positive and here it will be negative. Yes or no? This is the first quadrant, second quadrant, third quadrant and fourth quadrant. So in the first quadrant, both delta S and delta H are positive. So when I say delta H is positive, I mean the process is endothermic. When I say delta H is negative, it means it is an exothermic process. Getting it not? So the process, I'm assuming that it is occurring at constant temperature and pressure, and if delta G is less than 0, the process will be spontaneous. Now they ask you, when delta S is positive, delta H is also positive, what we should do so as to make the process spontaneous. Okay, so we should do one thing. I mean, remember, it's a shortcut basically, since we don't have time to give the explanations completely. So I'm giving a shortcut out here. In this case, if delta S and delta H both are positive, please increase the temperature. At higher temperature, the delta G will become less than 0. So process will be spontaneous if you are in the first quadrant. If you are having higher, increase the temperature. This T increase means higher temperature. This means actually T higher. T higher, okay? And over here, the process is always spontaneous. If it is an exothermic process and the entropy is increasing, the process will always be spontaneous, whether low temperature or high temperature. And once the process begins, it will go to the completion. Getting it? Over here, since these two quadrants are opposite, and in this quadrant, basically, the temperature has to be higher for the process to be spontaneous. Over here, if you want delta G to be less than 0, please have the lower temperature. T should be lower. Decrease the temperature and the process will be spontaneous automatically. Yes or no? And since these two quadrants are also opposite, over here it is always spontaneous, whether low or high, and here it is always non-spontaneous. The process never occurs over here, whether low or high. Yes or no? You're getting a not? So whenever delta H is positive and entropy is decreasing, the process will never be spontaneous. But when delta H is negative and delta S is also negative, remember that you want the process to be spontaneous, please decrease the temperature. Please decrease the temperature and the process will be automatically spontaneous. Yes or no? So let's do one thing now. So whenever they ask you a question, like say delta G equal to delta H minus T delta S, this though we know now. Now they want to ask you that at what temperature the process will be spontaneous or not. In that case, first of all, put it equal to 0. When you put delta G equal to 0, we are at equilibrium. So from this equation, you'll find out that T will be equal to delta H upon delta S. This temperature will be the temperature at equilibrium. Yes or no, beta? Yes or no? So say I'm saying this temperature, for example, in a given question comes out to be say 500 Kelvin. Is say 500 Kelvin. Are you getting or not? Now see, depending on now that whether you are in first quadrant, second, third, or fourth quadrant. So tell you one thing. This is the temperature at equilibrium, and suppose I am in this quadrant, first quadrant, where delta S and delta H both are positive. In the question they gave, the delta S and delta H both are positive. At what temperature the process will be spontaneous? I mean, first option, T equal to 500 Kelvin. Second, T less than 500 Kelvin. And third, T more than 500 Kelvin. Come on. Which answer you will mark? Both are positive if in the question. The T has to be more than 500. Remember that. Higher than the equilibrium. Are you getting it, everyone? Third one, yes. T has to be more than 500. Now, the same question, I mean, we are getting T equal to say 500 Kelvin. Now, if I am over here, at what temperature you believe the process will be spontaneous? If I am in the second quadrant, come on. At what temperature the process will be spontaneous? Come on. Always. Yes, it will be always spontaneous. Now same thing, but I am in the third quadrant where temperature we are calculating is 500 at equilibrium. In the third quadrant, but you have to decrease the temperature. So temperature should be less than 500 Kelvin. 500 Kelvin. Is that clear? Yes. And over here in the fourth quadrant, you do whatever, whether above 500, at 500, below 500, the process will never be spontaneous. Yes or no? Okay. Are you getting that or not? So let me give you a question now. Say the question says that we are having say delta H is given as 40 kilojoule and delta S is given as say 100 joule per Kelvin. 100 joule per Kelvin. Now tell you one thing, at what temperature range the process will be spontaneous? Come on. For that I should do one thing, T will be equal to delta H upon delta S. This is kilojoule, this is joule, so I should match the unit. 40 into 1000, this will become joule and this will be 100. So this is gone, this will be 400 Kelvin. So this is the temperature at equilibrium. Now at what temperature you believe for this given data the process will be spontaneous? The process will be spontaneous. Come on. I mean, any temperature above 400, maybe 500, 450, 460, whatever it is, the process will be spontaneous. Now, say if I say, say we are having minus of 40 kilojoule, sorry, minus of 40 kilojoule. Now, what do you think? At what temperature range, I mean, the process will be spontaneous? Instead of 40 kilojoule. This is now minus 40 kilojoule. Now see that in which quadrant you are. Earlier we were in the first quadrant. So T was supposed to be more than 400. Now this is delta H, this is delta H, and this is delta S, and this is delta S. So in which quadrant we are? We are now in second quadrant. Entropy is positive, but delta H is negative. Delta H is negative. We are here. Here always, at any temperature, the process will be spontaneous. Okay? Always is spontaneous. Now if I put it like, say, this thing, minus of 4, minus of 100, both have become negative. Both have become negative. Under what temperature range? The process will be spontaneous. Now we are in the third quadrant. Over here. Here the T should be less than 400 Kelvin. Anything like 300, 200 Kelvin will be the right answer. Yes or no? Decrease the temperature. Less than 400 Kelvin. And suppose I make it plus 40 and this is minus 100. I am in the fourth quadrant now. In the fourth quadrant, do whatever. The process will never be spontaneous. It will never be spontaneous. Yes or no? Is that clear? So the delta G and delta S part are okay or not? It will be non-spontaneous. Correct. Okay, now let us come to the Le Chatelier's principle. Okay, so I'll make it very simple, bache. I'll make it very simple for you people. Say, understand. We'll play this YouTube game. Remember that. Imagine of pouring water, and you have to focus here. You have to focus here, beta, है ना? On this horizontal branch. Now see that if I pour water from here, if I'm pouring water from here in this horizontal branch, the water will move towards right or left. Jaldi likhna bachcho yaar. Write faster if possible. The water will move towards right or left. Okay, I mean, it will move towards right. Focus on the horizontal branch itself. And if I pour water from here, it will move towards left. If I take out water from here, it will move towards left. And if I take water from here, it will move right. Agree or not? That is it. Okay. Now remember that this part is reserved for reactants. That means you will be pouring reactants from here and taking out the reactants from here only. And this part is reserved for products. That means you can add products from here and you can take out the products from here itself. Is that clear? Chalo aao. ठीक है now. So let's see what will be the effect of adding number of moles or weight of reactant or products. है ना? See that stuff. So we are having A plus B giving you C plus D. If I increase the number of moles of A, in which direction the equilibrium will move? Right hand side or left hand side? If I increase the concentration of A or number of moles of A, whatever you see that. So since A is a reactant, I can increase the A by putting A inside the system. And if I put the A inside system, it will move forward. That means equilibrium will shift forward. What is the meaning of that stuff? That A will react with B to give you more C and D. More and more products will be formed. If I increase the concentration of B, since B is also a reactant, and for reactant only this side is reserved. So I'll be pouring B again from here and reaction will move forward. That means I'll get more and more of product. Is that clear? But if I increase the concentration or number of moles of C, since C is out here, I can increase C by putting C inside. And in that case, it will move backward. The reaction will move backward. That means C will react with D to give you more and more of B and A. Agree or not? Similarly, if I increase D, what will happen? Since D is a product, it will be also increased by putting inside from here itself. It will move backward. Achha, who will tell me now? If I decrease the concentration of A, what will happen? If I decrease the concentration of A, or if I take out the number of moles of A will be taken out from here only. If I take out A from here, it will move backward. Agree or not? And if I decrease C, or take out C or decrease the concentration of C, for that I have to take out from here only. If you take out from here only, direction moves forward. बच्चों पहले बताओ यार ये समझ में आया कि नहीं आया? Have you got this thing or not? Write faster. Who can write faster, please? Fastest fingers first. अबे आज ही लिखोगे यार, जल्दी लिखो यार, तुम लोग कितना टाइम लगा रहे हो यार? अच्छा, here very important thing, that very important stuff, very important stuff, that pure solid or pure liquid will have no effect whatsoever on the equilibrium. No effect whatsoever. Getting it? That means this thing is valid only for the gases or for the solutions, not for pure solid, not for pure liquid. Okay? Now, let us come to the temperature part, very important. So remember that when we speak of temperature, we have to speak of heat also. Hai na? When I speak of heat, I mean endo and exo. So let me talk about endo and let me talk about exo separately, beta. Okay? To discuss the effect of temperature. Say we have A plus B giving you C plus D, and here also A plus B giving you C plus D. Now see, in endothermic reaction, you have to supply the heat. So what do you supply? We supply basically reactant. So heat will be written on the side of reactant. Anything which is supplied is called reactant. Yes or no? In exothermic reaction, heat is evolved, heat is produced, and whatever is produced is called product. And whatever is product will be written on the right hand side. So for exothermic reaction, heat will be evolved, will be produced. So I'll write down heat on the right hand side. Is that clear? Now, if I have to increase the temperature, the only way to increase temperature is to put heat inside the system. So if you put heat inside system, reaction moves forward. Agree or not? So in endothermic reaction, if you increase temperature, the reaction moves forward. Agree or not? That means more and more of product will be formed. But if you increase temperature in case of exothermic reaction, to increase temperature, I have got only one clue, and what is that? I have to put heat inside the system. And if I put the heat inside the system, the reaction moves backward. Are you getting it? Equilibrium shift toward the reactants. But if I decrease temperature here, in the endothermic case, to decrease temperature, I have to take out heat outside. The temperature will decrease, but if I take out heat outside, the reaction moves backward. It will follow that stuff. Yes or no? And over here, if I decrease temperature, that means I have to take out the heat. You take out heat, reaction moves forward. They both are opposite. Is that clear or not? The effect of temperature for endo and exo. Like say one more thing. Remember that pressure and volume. If I see we have a piston, for example, I can change the pressure and volume by shifting the piston. So if I push the piston, if I'm pushing the piston, pressure will increase, but volume will decrease. They both are inversely proportional. P and V are inversely proportional. But if I pull the piston, the pressure will decrease inside and the volume will increase. Yes or no? है ना? So, but I mean, we can change. I'm sharing the tricks with you people. We can change the pressure and volume with the help of piston only. Getting it? And where you will put the piston? You will always put the piston where the number of moles are more. Where? Always, blindly, where number of moles are more. That means gaseous, na? Gaseous moles are more. For example, over here, we have got A plus B giving you C. Okay? And I'm giving you one more thing over here. Say A giving you B plus C. And I'm also giving you third case where we are having A plus B giving you C plus D. Okay. Now, first of all, tell me where I'll put the piston. I'll put the piston where number of moles are more. Here. Here, number of moles are more here. 2. Here, the number of moles are same. Delta Ng is equal to 0. So there is no need of piston. If I can't put piston, I can't change pressure. I can't change volume also. So pressure and volume will have got no effect when number of moles are same. Gaseous moles are same. Okay. Now see that if I increase pressure, I have to push the piston. If I push the piston, it will come down and things will move forward. So the reaction will move forward. Yes or no? And over here, if I increase the pressure, the only way to increase pressure is what? Push the piston. Push the piston, it will come down, things will move backward. Yes or no? Equilibrium shifts backward. Here though there will be no effect. Since I can't put the piston, piston can be put only when the number of moles are higher on one side. Yes or no? And if I decrease volume, for example, volume can be decreased by pushing the piston. If I'm pushing the piston, reaction moves forward again. You increase pressure or decrease volume is one and same thing. One and same thing. Yes or no? And here also, if I decrease volume, decreasing volume can be done by pushing the piston. So push the piston, it will move backward again. And or moreover, you can say increase in pressure or decrease in volume is one and same thing. Is that clear? Is that clear or not? So remember that when handling the pressure and volume questions, put the piston first of all. Where the number of moles are more. Whose moles? Gaseous moles. Pure solid, pure liquid, don't take them into account while handling pressure questions, okay? And when the number of moles are same on both the sides, pressure, volume will have got no effect whatsoever. Now, the last one is that effect of inert gases. Effect of inert gases. So I am sharing a trick with you people. I mean, you people have heard about the Battle of Mahabharat. The Battle of Mahabharat was fought between the two parties, Pandavas and Kauravas. Pandavas were lesser in number, Kauravas were more in number. There are 100 of them. Even if I talk about the brothers, Pandavas were 5 in number. If I talk about brothers only, And in that battle, the superhero, Lord Krishna, took the sides with Pandavas. So what I'm saying, Lord Krishna came into the war from which side? From the side where the number of people were less. Actually, the good people are lesser in number always. So God will help the good people who are lesser in number. So here I'm equating the ideal gas. Say for example, helium. Put helium gas equivalent to Lord Krishna. And Lord Krishna will now come from which side? Where the number of moles are less. Which moles? Gaseous moles are less. Say for example, we have got A plus B giving you C. And here we have got A giving you B plus C, and one more case where you've got A plus B giving you C plus D. Are you getting that? So now, before I move into this point, I want to tell you one more thing, and that is that when handling the noble gases or the inert gases, there are two conditions. One is constant volume. At constant volume, so nothing will happen, no change will occur at constant volume. Whatever discussion we are going to undertake, that is at constant pressure. At constant pressure, whatever I am going to discuss will occur. But if in the question they give you constant volume, nothing will occur, no change whatsoever. Remember that. Okay. Now come, this discussion is at constant pressure. The pressure is constant. So if I add helium, neon, krypton, nitrogen, all the inert gases, over here, then in that case, Lord Krishna will enter from the side where the number of particles are lesser. So from here, and the reaction moves backward. That means equilibrium will shift backward. In this case, number of moles are less here. So Lord Krishna will enter from here and the battle shift that side now. Yes or no? And over here, when the number of parties or particles are same, in that case, Bhagavad Gita says that Lord Krishna will not come to help you. You have to take care of yourself. No help is coming out whatsoever. That means if delta Ng is 0, any inert gas now can't change anything. Yes or no, beta? Is that clear? So can we do some questions now? So let's do some questions now. बेटा देखो ऐसा है, we have got NaNO3 giving you NaNO2 sodium nitrite plus half O2. Now tell you one thing, I mean, if I increase the number of moles of sodium nitrate, if I increase the number of moles of sodium nitrate, the equilibrium will shift forward or backward? Forward, backward. The answer is no effect, because it is pure solid. This is also pure solid. So even if I add sodium nitrite, there will be no change. Pure solid, pure liquid, they don't change the equilibrium situation. Yes or no, beta? Now this is basically a dissociation reaction. So that means you have to supply heat. This is an endothermic reaction. It is an endothermic reaction. Yes or no? So now if I increase temperature, increase in temperature can be done by putting heat inside. If I put the heat inside, reaction moves forward. So on increasing temperature, equilibrium will shift forward. Yes or no? Now this is pure solid, this is also pure solid. So now if I want to increase pressure, now pressure can be increased by putting the piston. Where you will put the piston? Where the number of moles are more. Here so there is nothing, but something is there. Half moles of O2 are here. Here is 0. Here is half. Half is more than 0. So I'll put the piston here. Now if I increase pressure, you can increase pressure by pushing the piston down. If you push the piston down, reaction moves backward. Yes or no? So in this case, reaction moves backward. Is that clear or not? Now, if I add helium gas, before answering any inert gas question, please make sure that you have satisfied the condition. Which condition? Either constant volume or constant pressure. So, helium gas at constant volume will have no change whatsoever. Helium gas at constant pressure. Now, the helium gas will enter from where? Where the number of moles are less. Here. So helium gas will come from here. Reaction moves forward now. It will move forward. Is that clear or not? Equilibrium shifts forward. More and more O2 will be formed from that point of view now. Okay. Now see one more thing. Let's have this thing as well. Let's have this thing. Twice SO2 plus O2 giving you twice SO3 and say heat. This is an exothermic reaction, for example. Now tell you one thing. If I increase the number of moles of SO2 is a gas. So SO2 can be increased by putting inside from here. It will move forward. More and more SO3 will be formed. Okay, now tell you one thing. If I increase the number of moles of SO3, which can be done by putting the SO3 from here, reaction moves backward. Yes or no? Chalo, if I increase temperature, for example, you can increase temperature by putting heat inside. Heat will come from here only. So it will move backward. In this case, reaction moves backward. Yes or no? If I increase pressure, for example, first of all, let me find out the number of moles. 2 and 1, 3 moles. Only 2 moles are here. Here we have got 3 moles, 2 and 1. So I'll put the piston here. Once I put the piston here, to increase pressure, I have to push down the piston. If you push the piston down, coming down, reaction moves forward. Yes or no? Yes or no? And one more thing, putting helium gas. But before answering the question of helium or any inert gas, make sure that it is not at constant volume. Helium gas at constant volume will have no effect. But helium gas at constant pressure, come on, helium gas at constant pressure. 3 moles, 2 moles, these are the Pandavas, lesser number. So helium will enter from here at constant pressure and reaction moves backward. Reaction moves backward. Yes or no? Is that clear? Is that clear to all of you? So that is more about this Lee Chatelier's principle. Try to solve those questions, and like one last topic is remaining, and that is called solubility product. But before I move to solubility product, but tell you one thing, have you understood what I have taught you right now regarding this Lee Chatelier principle? You will be able to handle almost all of those questions. Is that clear to all of you? Okay. So let's go to solubility product now. Okay. Yeah, this is important one. Okay, let's see now. Regarding this solubility product, है ना, but you have to be careful that when to use what stuff, है ना. So there will be a question of purity and the question of impurity. That when I say purity means only the given salt is there. For example, they talk about AgCl, it will be AgCl only. There will be no impurity like NaCl into it or KCl into it or a base or acid into it. Is that clear? Not? So whenever it's the question of purity, boys, you can apply the formulas directly. Say for the salt like AB. Remember that solubility product, this as a concept is applicable for sparingly soluble salts. Sparingly soluble salts. Okay. So for the salt like AB, the solubility product KSP is given as S square. For AB2 salt, it is given as 4S cube. AB3, it is given as 27S4. And for A2B3, this is given as 108 into S to the power of 5. These formulas, they are already present in your copy. Your teachers must have taught that stuff, na? But they are applicable only when the salt is pure. There is no impurity added to it. No other salt, no acid, no base, nothing. Only this given salt is there. Yes or no? If it is like maybe say AgBr, only AgBr is there. There is no impurity like HBr into it or KBr into it. Okay? And when they give you impurity, but these formulas are not applicable. These formulas are not applicable when they put impurity into it. Are you getting that? Then only law of mass action is applicable. Law of mass action is applicable. Say what I'm saying is that, say if only AgCl is given, so this AgCl, which is solid, will dissolve to give you Ag plus and Cl minus. So for one Ag plus, I'll get one Cl ion. And suppose the solubility is S. So what is solubility? Nothing but concentration in terms of molarity. So this is say S. This will also be S. In that case, the KSP will be Ag plus into Cl ion upon AgCl. AgCl is a solid and solid has an active mass of 1. So we don't take solid into account. Solid is useless. That is called KSP. This thing is called actually law of mass action. This is called law of mass action. But here, since they both are having the same concentration, I can write down S into S, that is S square. But in case of impurity, they will give you AgCl, which is going to give you Ag plus and Cl ion, and I'm putting some NaCl into it. So it will give me Na plus and Cl ion also. Like say now, NaCl will completely dissolve. Now, since Na plus is not the part of this equilibrium, nor it is a common ion. Are you getting that or not? So suppose the solubility is suppose say S. So both will be SS, but since now I am having like say Cl negative, like so this was say 1 molar. So I'll get 1 molar of this thing and 1 molar of this thing. Now in the solution, we have got how many Cl ions? 1 plus S. So KSP actually will be what? Ag plus into Cl ion. Are you getting that? So this will be like say maybe say S dash and S dash and into 1 plus S dash. So this formula is not applicable now. This thing is not equal to this thing. Is that clear or not? Yes or not? So I can only apply law of mass action here, but not the formulas directly. We can apply formula directly when only purity is given. Now the only question is that, sir, how will I come to know whether it is purity or not? So I'll tell you what. Purity, and we have got the case of impurity. Whenever only KSP or the concentration of any of the ion, directly or indirectly, only one of them is given, then that is the case of purity. But when they give you the KSP and the concentration of one of the ion, both of them are given. In that case, assume it to be 100%. I'm telling you, it is a case of impurity in general. Getting it or not? So only when either KSP is given or only the concentration is given, then we can say this is a question of purity. You can apply all those formulas, S square, 4S cube, 27S4, all that stuff. But if both of them are given, you are not going to apply the formula. You will apply only what? Law of mass action. Is that clear? Clear or not? So let's solve some questions directly. Na? See that now. So I'm giving you the KSP of AgCl is given as 10 to power of minus 10. Only this thing is given. Only this thing is given. Case of purity, impurity. Case of purity or impurity. Come on. Only one thing is given. It's the case of purity. Now, I know that for AgCl, it is a salt of category AB. So the KSP will be actually S square. How much? 10 to power of minus 10. S will be 10 to power of minus 5 molar. Yes or no? So that is the solubility. Now this S is what? Nothing but concentration of Ag plus, which is also equal to concentration of Cl negative. How much? 10 to power of minus 5 molar. Yes or no? Very good. Very good. Now let's say one more thing. I'm giving you the salt is given as HgCl and concentration of Cl negative is given as 10 to power of say minus 4 molar. Can you find out the KSP? Can you find out the KSP? Only one thing is given. Only one thing is given. It's the case of purity. When I got a case of purity, I can apply what? Formula directly. It's a salt of what? AB category. So KSP will be S square. This thing is what? Nothing but S only. Yes or no? So this will be 10 to power of minus 8. So KS will be 10 to the power minus 8. Good. Very good. Very, very good. We can do those questions directly. Now let's do something more. So I'm giving you KSP of magnesium hydroxide is given as 4 into 10 to the power of minus 12. Can you find out the solubility? Can you find out the solubility? Come on. Come on. This is a case of purity or impurity? It is a case of purity. Because only one thing is given. Only KSP is given. Yes or no? So for this AB2 category salt, KSP actually will be 4S cube. 4 into 10 to the power of minus 12. So 4 and 4 cancels. S will be 10 to the power of minus 4 molar. Yes or no? Yes or no? So if you will break this down, magnesium hydroxide will give you what? Magnesium ions and twice of OH ion. That means this will be S and this will be 2S. For every one magnesium ion, we will have 2 hydroxide ion. So what is the value of S? It is 10 to the power of minus 4 molar. What is the concentration of OH ions? 2 into 10 to the power of minus 4 molar. Yes or no? Yes or no? Now, in this same question, they can ask you, come on, find the pH of the given solution. Find the pH. If they give you KSP, can you find out the pH? Yes, I can find out the pH because now I have got OH ion concentration. So if the OH ion concentration is given as 2 into 10 to the power of minus 4 molar, I can find out POH. POH will be what? 4 minus log of 2 will be 4 minus 0.3 will be 3.7. 3.7. Yes or no? And if POH is 3.7, pH will be 14 minus 3.7 will be 10.3. Yes or no? 10.3 or not? Okay, it's okay, no problem. Can you handle these questions directly? Now, if they give you the pH of the given solution, can you find out the KSP now? Yes, I can. From pH, I'll go to POH. From POH, I'll go to OH ion concentration, which is nothing but what? 2S. This is nothing but what? 2S. From here, I'll find out S. When I find out S, I'll find out 4S cube also. Yes or no? Yes or no? Okay. So let's do some questions now. Let's say the magnesium hydroxide is given. They're saying the pH of this is say given as say 10. pH is given as say 10. Can you find out the KSP of this stuff? But only concentration is given. This is a case of purity. This is a case of purity. But from pH, first let me find out POH. How much? 4. From POH, I'll find out OH negative. How much? 10 to the power of minus 4 molar. Yes or no? Since it's a case of purity, I know that this is magnesium hydroxide giving me magnesium ions and 2 OH ion. Yes or no? So concentration of OH ions is what? 10 to the power minus 4. So this is S and this is what? 2S. So 2S is actually 10 to the power of minus 4. Will you all agree? Will you all agree? And that S will be how much? 10 to power of minus 4 upon 2. That will be 5 into 10 to power of minus 5. Agree or not? So once I find out the S value for this AB2 category salt, when this is the case of purity, KSP will be 4S cube. I can directly apply the formula. So 4 into S cube, 125, 10 to power of minus 15. This is what? 500. 500 into 10 to power of minus 15. What's the answer? Come on. This will be 5 into 10 to power of minus 13. Will you all agree with me that? Yes, very good. Very, very good, bache. Satya, wonderful. Very good, brilliant. Is that clear to all of you? Now, see that when they give me the case of impurity, they can give me the concentration directly or indirectly. Say, for example, we have got AgBr, or say, let's take AgCl itself to make it simple. For AgCl, they have given KSP equal to 10 to power of minus 10, and they have also given the Cl ion concentration to be 10 to power of minus 1 molar. They're saying find out the new solubility or the Ag plus ion concentration. Now see, both KSP and concentration of one of the ion is given. This is the case of impurity. I cannot apply the formulas. I can only apply the law of mass section. So AgCl will give me Ag plus and Cl ion. So KSP will be actually Ag plus into Cl ion. Law of mass action is only available for me. Yes or no? This is a case of impurity. So KSP will be 10 to power of minus 10. So Ag plus into 10 to power of minus 1 will be 10 to power of minus 10. So Ag plus will be 10 to power of minus 9. Yes or no? Minus 9 molar. Yes or no, beta? When both of them are given, don't apply the formulas, only apply law of mass action. Is that clear? Achha, if I give you Cl negative 2 is 10 to power of minus 2, still both KSP and concentration of one of the ion is given. I will not apply the formula. I'll go with the law of mass action. Same thing, but this will become 10 to power minus 2. This will become 10 to power minus 8. That's the answer. As simple as that. As simple as that. Will you all agree? Good. Very good. So let's do one more question. Let's do one more question. So what I'm saying, I'm giving you KSP of magnesium hydroxide. I'm giving you say 10 to power of say minus 11, and I'm giving you magnesium ion concentration. I'm giving you say 10 to power of minus 1 molar. So can you find out the pH of solution? Can you find out the pH of solution? You can definitely find out if you find out the OH ion. Now both of them are given. KSP is also given and magnesium ions are also given. This is a case of impurity, and for the case of impurity I'll have only law of mass action. So I know that magnesium hydroxide will give me what? Magnesium ions into hydroxide ions, 2 of hydroxide ions. Na? So that means KSP will be magnesium ions into OH ions whole square. The stoichiometric coefficient goes into power. Na? So this is given as how much? 10 to power of minus 11. This is 10 to power of minus 1 into OH ion whole square, 10 to power of minus 11. This will be 10 to power of minus 10, but this is OH whole square. So OH negative will be 10 to power of minus 5 molar. If you have got OH ion concentration, what will be the POH? Come on. POH will be 5, and if POH is 5, pH will be 9. 14 minus 5 will be 9. Yes or no? Can you handle this? Okay. Okay. So let's do the one last question. One last question. Let's do that. So like it will be. Say again, I'm saying the KSP of magnesium hydroxide I'm giving you is say 10 to power of minus 12, and pH of the solution I am giving you is say 10. pH I am giving you 10. Can you find out the magnesium ion concentration? Can you find out the magnesium ion concentration? So let's say we are having magnesium hydroxide giving you magnesium ions and twice OH ion. Both of them are given directly, indirectly. POH will be how much? POH will be 4. Agree or not? And if POH is 4, OH ion are given as 10 to power of minus 4. Yes or no? Yes or no? है ना? So only, and this is the case of impurity. Both are given. So KSP will be magnesium ions into OH ions whole square equal to 10 to power minus 12. So magnesium ions into OH ion whole square will be 10 to power of minus 8. 10 to power of minus 12. Cancels up. So this will be 10 to power minus 4. So magnesium ion concentration will be 10 to power of minus 4 molar. Yes or no? Yes or no? So will you be able to handle these things? One thing is also remaining, and that is that which can go into oxidation and reduction. Say for example, if I talk about sulfur, the highest oxidation state of sulfur is say +6, and the lowest oxidation state of sulfur is say -2. Example of this can be like say H2S, and we can have something over there, maybe say SO2, and here we are having say SO3. SO2 here is having say S and say +4. Now remember that if an element is already in the higher oxidation state, it cannot go further. It cannot lose electron. It cannot donate electron. This is not possible. What it can do, it can accept electron. If it will accept electron, it will be an oxidizing agent. Yes or no? It cannot give the electrons. It can only accept electron. Anyone which is accepting electron will be an oxidizing agent, and it will be coming over here maybe. It can come here also. Yes or no? From +6, if it accepts 2 electron, it will come here. If it accepts 8 electron, it will come here. And H2S contains S and -2. I mean, you cannot go there. You cannot accept electron now. That means you simply cannot go there. What you can do is now you can donate electrons and can go there. So if you are donating electrons, you are a reducing agent. You are a reducing agent. Getting it? So that means this can go here by -2 to +4 by donating 6 electron. It can go from here to here from -2 to +6 by donating 8 electrons. By donating 8 electrons. Yes or no? So this will be acting as a reducing agent, this will be acting as the oxidizing agent. But this sulfur in SO2 can go here also, can go here also. I mean, if it goes there, it will have to accept electron. It will have to accept electron. How many electrons? +4 to -2. It will have to accept 6 electron. If it is accepting 6 electron, it is acting as an oxidizing agent. Who? SO2. And if it is going there, it is donating electrons. How many electrons it will donate? It will donate 2 electrons. So it can act as a reducing agent. So that means anything which is in the intermediate oxidation state can act as a reducing agent as well as an oxidizing agent. Yes or no? Yes or no? And if you are already in the lowest possible oxidation state, you can simply act as reducing agent but not an oxidizing agent. You cannot accept electron anymore. But over here, if you are in the highest possible oxidation state, you cannot lose electron. You cannot act as a reducing agent. You can all do what? Accept electron and can act as an oxidizing agent. Yes or no? And regarding disproportionation reaction, yesterday there was a question that K2MnO4 giving you MnO4 negative and say MnO2. So here Mn is in +6, this is +7, and this is say +4. Disproportionation reaction means when a single species can go for higher oxidation state and for a lower oxidation state. So Mn is going from +6 to +7 and from +6 to +4. Yes or no? When the single element is reduced and oxidized, that is called disproportionation reaction. Yes or no? Yes or no? There was a question that CuBr giving you say CuBr2 and Cu. So here this copper is actually +1. Here it is say +2 and 0. So from here to here it has get oxidized, and from here to here it has got reduced. So if the same element get oxidized and reduced, this will be called disproportionation reaction. Yes or no? And the opposite of that, when the same element is in two different oxidation state and comes to one, this is called compo-proportionation reaction. Com-proportionation reaction. Reverse of disproportionation is what? Com-proportionation reaction. Is that clear? Okay, thank you. In that case, students, I'll take your leave. I hope this session was useful for you people. Keep on doing revision and don't do extra things. Stick to whatever you have done already and practice it multiple times. You get the confidence. Confidence is very much required right now. Hai na? Okay. Chalo, I wish you all the best. God bless you all. Take care. Bye-bye. Bye.